Good evening, everyone. Welcome to Seminar 9. In this seminar, I'll be teaching you how to solve problems in the frequency response chapter. So, there are 4 questions in this seminar, if you can see from the Seminar 9 question uploaded in eClass. Instead of teaching all the theory first and then solving, I'll just teach whatever is required as I'm solving these problems. So, let's get into the problems straight away. Let me open the question paper on the screen so that it's easier for me. Yeah. So let me read the question first. So in the given transfer function of a standard feedback system, so we have been given the process transfer function 1.5 by 10s plus 1, and then the valve transfer function minus 10 by s plus 1, and then there's a measurement device transfer function e power minus 0.5 to s, and then we have been asked to assume that there is a PI controller in the system with Kc minus 0.72 and integral time 3.74. So we have to compute the following. So the frequency response of the open loop transfer function and analyze the stability using Bode stability criteria. And if a sinusoidal set point change of 1.5 sine 0.5 t is applied, what is the amplitude of the measure output signal under open loop, that is the second subdivision, and under closed loop. So we have to see if we supply a sinusoidal set point, what will be the amplitude of the measured output signal under both open loop and closed loop conditions. Let me go to the next page, then I'll start solving the problem. The color, yeah, black. So from the information given in the question, if I draw the basic layout, so we have a controller transfer function, which is a PI controller, and then we have a valve, and then we have been given a process transfer function GP, and then in the question we have been given a measurement transfer function, so GM. We'll be always using a negative feedback. Yeah. So this would be the basic structure of the feedback loop. And now if I write the open loop transfer function, G open loop, it is just going to be the sum of, the product of all the blocks. GCFS into GVFS. Yeah. And if I substitute all the values, given in the question, what I would get is, so the controller's transfer function should be, let me write it down here, because it is a PI controller, Kc plus Kc into 1 plus 1 by tau y into S. So Kc and tau y has been given in the question, so I'm substituting it directly. 1 plus 1 by 3.74 S, and then the valve transfer function minus 10 by s plus 1, and then the process transfer function 1.5 by 10s plus 1, and then I'll write the delay part separately so that it will be easier for us to calculate. Yeah, so this will be our open loop transfer function in S domain. And for doing our frequency analysis, all we have to do is substitute S is equal to I omega or j omega. I'll use I omega into the original open loop transfer function, and then we can compute the amplitude ratios and the phase angle and all the other characteristics of frequency response analysis. So let me substitute S is equal to I omega first. Before that, I'll just do some basic simplification here. The rest will be the same, minus 10 by s plus 1. So now we substitute S is equal to I omega. So the amplitude ratio of the open loop transfer function of the open loop transfer function will be because we substitute I omega in the place of S. So let's solve this. So the RHS, so amplitude ratio of the open. So wherever there is an S in the original transfer function, I substitute it with I omega 0.72 74 I omega plus 1 by 3.74 I omega, and then minus 10 by I omega plus 1, and then 1.5 by 10 I omega plus 1. Then in the numerator we had the delay term, 0.5 I omega. Okay, I missed a negative sign here, minus 0.72. So it doesn't matter because the absolute value of a real number will be the real number without the sign or the positive. We just remove the negative sign. So we know that the absolute value of a complex number a plus ib is equal to a square plus b square. It's a square root of the sum of the squares of the real part plus the imaginary part. So we'll apply this formula here to compute. So amplitude ratio is equal to 0.72. Then we have square root of 3.74 square omega square plus 1 divided by, it will be square root of 3.74 square omega square, which will be 3.74 omega again, and then into the absolute value of minus 10 is 10 by root of omega square plus 1 into 1.5 by 10 square omega square, so that will be 100 omega square plus 1 into the absolute value of e power a negative term minus 0.5 I omega, that will be equal to 1, because this is in the polar form, polar coordinate form. So if I expand this, so e power minus I theta is equal to cos theta minus I sin theta. So if I take the absolute value, this will be equal to cos square theta plus minus sin theta the whole square, which will be equal to root of cos square theta plus sin square theta, which is equal to root 1. It will be 1. So always when we are taking the modulus of the e power minus I theta term, we'll be having 1. So we'll be needing this result for the subsequent problems as well. So I've just shown the explanations here. So this will be, so this is our amplitude ratio. And then now we'll compute the phase angle of the open loop transfer function, which is represented by phi of open loop. So again, from complex number theory, so if you have a complex number a plus ib, the angle subtended at the origin will be tan inverse the imaginary part by the real part. So this can be rule 1, rule 2. And if you refer to the class notes, there are some properties of the argument. So we'll be using that here. So let me start. So the real number will lie on the x-axis, so there will be no for 0.7. So let's go term by term. So first we'll have a 0, and then 3.74 I omega plus 1, that tan inverse of b by a. B is 3.74 omega. And arg of z1 by z2, which is equal to arg z1 minus arg z2. z1 and z2 if they are complex numbers. So in that case, we'll be using that formula here. So for the denominator, we'll have a negative sign, tan inverse. B is 3.74 omega, and we don't have a real part, so by 0. And then again for 10 there will be will be 0 again, minus 10, and then minus tan inverse of omega by 1, which is omega, and then 1.5 will not have an argument, minus tan inverse of b by 8, which is 10 omega. And the last part is, so let me erase this out and I'll show you. Let me change the color so it's easier. So if you see from here, tan inverse of b by a, the imaginary part is minus sine theta, by the real part is cos theta. So sine by cos is tan, so we have tan inverse of minus tan theta, sorry. Minus tan theta. So tan inverse and tan are inverse functions, so they cancel each other, and what we have is minus theta. Finally. So if we go back to the solution again, so for e power minus 0.5 omega, what we'll have is minus 0.5 omega. So if you write everything down, tan inverse 3.74 omega. So tan inverse of infinity is pi by 2. So I'm just substituting, and then tan inverse omega minus tan inverse 10 omega minus 0.5 omega. So this will be the equation for the phase angle, the open loop transfer function. And now we have been asked to do stability analysis based on frequency response analysis. So we write stability analysis. So to do the stability analysis, first we have to find the phase crossover frequency omega, and then substitute the phase crossover frequency. So okay, let me show. So the phase crossover frequency can be found out by assuming that the phase angle is equal to negative 180 degree, and solve. And then if we substitute the phase crossover frequency into the amplitude ratio of the open loop transfer function, what we get is the critical amplitude ratio. So if critical amplitude ratio is less than 1, system is stable. Equal to 1, marginally stable. If it's greater than 1, it is unstable. So we'll do the following to comment on the stability of the system. So first we find phase crossover frequency. For that we have to use the equation of the phase angle here. Tan inverse 3.74 omega minus pi by 2. Tan inverse omega tan inverse 10 omega minus 0.5 omega, and now we have to substitute the phase angle is equal to minus 180 degree to get the crossover frequency. So minus 180 degree. So when you substitute in the it should be minus 180 degree will be pi radian, because the unit of crossover frequency will be in radians per minute or radians per second. So so when you solve the equation, minus 180 degree has to be minus pi tan inverse 3.74 omega minus pi by 2 minus tan inverse omega minus tan inverse 10 omega 0.5 omega. And now the only variable is omega, and you should note that here omega is equal to omega crossover frequency because we have substitute minus 180 degree on the left hand side. So if you solve in a scientific calculator or in MATLAB, what you will get is the crossover frequency is equal to 1.15. And if you look at the question, there has been no units mentioned, so you can just put radians per minute. So now that we have the crossover frequency, we can substitute this into the amplitude ratio of the open loop equation and then compute the critical amplitude ratio. So the amplitude ratio of the open loop system at the crossover frequency is equal to the critical amplitude ratio. And if you do the math, if you substitute omega is equal to 1.15 into, so let me call that equation 1. So if we substitute omega is equal to 1.15 in equation 1, and if you do all the simplifications, we'll get the critical amplitude ratio is 0. So I already checked all these calculations, so you can try doing those calculations. If you don't get it, you can drop me an email. I'll show you how to do the calculations. Okay, I'm confused. Okay, 0.63. This is what you will get. So here the critical amplitude ratio is less than 1, so the closed loop system is stable. So this is how we'll be doing the stability analysis through the frequency response analysis route using the Bode stability criteria. And now we'll go to the second subdivision. So in second subdivision, we have an input signal u is equal to 1.5 sine 0.5 into t. So this is so the general form of a sine input is a sine omega t. So if you compare to the general form, we get the amplitude is 1.5, the amplitude of the input is 1.5. Frequency of the input is 0.5 radians. So we have the equation for the amplitude ratio, the open loop system from the previous subdivision. So we have already computed, which was equation 1. And to compute the amplitude ratio numerically, all we have to do is substitute the frequency of the input signal into the amplitude ratio equation. Substitute omega I is equal to 0.5 to omega in equation 1. You'll know all the terms of the equation, and then if you do the simplifications, you'll get the amplitude ratio as 2.14. Amplitude ratio is nothing but the ratio of the output amplitude by the ratio of the input amplitude. Amplitude of the output signal by the amplitude of the input signal. And the amplitude of the output signal is the amplitude ratio into the amplitude of the input signal. So from the question, we know that the input signal is of amplitude 1.5. So the amplitude of the output signal will be 2.4 into 1.5, which will be equal to 3.21. So if you look at the question B, so under open loop conditions, we have been asked to find what is the amplitude of the measured output signal if the input signal is 1.5 sine 0.5 t, and so this will be the answer for the second subdivision. And now we have to do the same thing. So what if the system is in closed loop form? In that case, what will be the amplitude of the output signal is our next question. So we are applying the same input, 1.5 into sine 0.5 t. So we know that the open loop transfer function was gc into gv into gp into gm. So the closed loop transfer function will be by 1 plus g over. Because we have a negative feedback. So this will be in S domain first, and then we'll be substituting S is equal to I omega, and then we can do the computations, other computations. So we know that the input amplitude is 1.5 and the input frequency omega is equal to 0.5. So the amplitude ratio in closed loop will be equal to So instead of plugging in the values and computing everything from scratch, we can just use a trick here. So we'll be substituting S is equal to I omega anyway. So the amplitude ratio So this offers a shortcut to compute the amplitude of the closed loop system. So we know that a complex number can be expressed in polar coordinates as if z is the complex number, then in polar coordinates it can be expressed as modulus of z e power minus I theta. So here we already know the modulus of z. Okay, so let me find a better explanation here. So I can erase this down so that it's easier to understand. Is equal to GC into GV into GP to GM by 1 plus GC into GV into GP to GM. And if you go to subdivision 1, we have the equation for the phase shift. So let's call it equation 2, because we'll be needing that to compute the theta. So let equation 1 be the equation of the amplitude ratio in terms of omega, and let equation 2 be the phase angle in terms of omega. Yeah, I missed it here, that's why I was not able to go further. So a complex number can be written in the polar coordinate form as, so z, it is a complex number, it can be written in the polar coordinate form as modulus of z to e power minus I into theta. So the modulus of z for this particular input frequency omega, so using omega, I is equal to 0.5, we can substitute it in equations 1 and 2. So the amplitude ratio will give the modulus of the complex number. We have already computed this in the previous step, which is 2.14. So 2.14, and then if we substitute omega is equal to 0.5 into the phase angle equation, we'll get theta is equal to minus 2.578. Please make sure all the units are in radians when you're doing the computations. And so now we can express the whole numerator in polar form. So it will become GCL into this term. So this is the open loop transfer function, right? So the open loop transfer function, so complex number expressed in polar form will be z into e power minus I theta. So e power (2.578 I). So this will, if we write it down in polar coordinate form, it will be easier for simplifications further, like I'll show. So now the amplitude ratio of the closed loop will be equal to I omega. I substitute 2.14 e power minus 578i divided by this can be further simplified as 2.14 minus 2.578 e per theta can be written as r cos theta plus I sin theta. So 1 cos here theta's value is minus 2.578. So cos of minus theta is cos theta. This is a trigonometric rule. So what we'll have here is cos 2.578 minus I sin 2.578 whole modulus. And now if we group it into real parts and imaginary parts, 2.14 into e power minus 2.578 I divided by 1 plus 2.14 cos 2.578 minus I sin 2.578 whole modulus. So now we can compute the modulus, the absolute value easily. So the amplitude ratio of the closed loop be equal to 2.14, and then we know that the modulus of e power minus theta I will be equal to 1 again, so divided by a square plus b square. So we have the real part square 2.578 square plus 578. And if we plug in all the numerical values of the cosine and sine, what we get is amplitude ratio of the closed loop will be 1.528. And we know that the input signal was u is equal to 1.5 sine 0.5 into t. So the input amplitude ai is 1.5. So the amplitude ratio of the closed loop from our computations, we get 1.528. Amplitude of the output is equal 1.528 into input amplitude 1.5, 2.29, and this will be the amplitude of the output signal under closed loop conditions. Yeah, the closed loop was slightly tricky because we had to write the numerator and denominator in polar coordinate form to make our computations easier. Otherwise we'll be having lengthier equations and it's really hard. And also if we write it in polar coordinate form, we can use the numeric values from whatever we have computed from the previous steps from the open loop conditions and substitute those values. So it has simplified our calculations to a greater extent. This completes question 1, and now let's go to question 2. So let me read question 2 first. A heat transfer process has the following transfer function. G of s is equal to 3 into 1 minus s by s into 2s plus 1. The transfer function is between the temperature, which is the output, and the inlet flow rate Q. If the flow rate varies sinusoidally with an amplitude of 2 liters per minute and a period of 0.5 minutes, what is the amplitude of the temperature signal after the transients have died out? So this is in fact it is similar to question 1. So the amplitude of the output signal T after the transients have died out is nothing but what is the amplitude of the output signal. So this is a different way of asking the question. So we have been given the following information. The amplitude of the input signal is 2 liters per minute, and we have been not given the frequency. Instead we have been given the time period of the input signal, which is 0.5 minutes. And the angular frequency omega I, the formula is 2 pi by Ti. So we have 2 pi by 0.5, 4 pi radian per minute. So the important thing to note here is we have not been given the angular frequency, but we have been given the period. So this is an important. So we have to compute the angular frequency before we can use it in our calculations. So now we know the amplitude of the input signal and the frequency of the input signal, and we know the transfer function G. So if you know the transfer function, the first thing we'll do is, so the transfer function is in terms of S. S into 2s plus 1. So we will substitute S is equal to I omega. So G of I omega into 1 minus I omega by I omega into 2I omega plus 1. So the amplitude ratio will be directly the absolute value. So we'll have 3 just like that, and then 1 plus omega squared divided by root of the real part of I omega 0. So we'll have And from the question we know that the input frequency is 4 pi radians per minute. If we substitute omega is equal to 4 pi, we'll get the amplitude ratio. So amplitude ratio is equal to 3 into root of 1 plus, I'm substituting 4 pi in the place of omega, so let me write it down here so it's easier. Okay, so amplitude ratio, we know that omega is 4 pi, so we substitute 4 pi 1 plus 4 pi squared divided by 4 pi into 1 plus 4, so 4 into 4 pi square. So if we compute, so we know that the amplitude ratio is the amplitude of is the ratio of the amplitude of the output signal by the ratio of the input signal. So 3 by 4 pi root of 1 plus 4 pi square and we know from the question that the input amplitude is 2, so we just substitute AI is equal to 2 and then cross multiply AI into the term right here, and if we do the simplification, you'll get the output amplitude to be 0.24 liters per minute. Yeah, the unit is important, it should be liters per minute, because in the question the amplitude is also in liters per minute. So the output amplitude, or the amplitude of the signal after the transient has died out, both of them carry the same meaning, so this will be the final answer. Okay, so let's go to the third question now. I think this seminar is a bit lengthy because we have 4 questions. Question 3. Let me take the solution. Yes. I missed a paper, I think. Okay. So let me read question 3 here. A process including valve and sensor transmitter has the approximate transfer function with time constant and delay in minutes. So the transfer function is 2 into e power minus 0.2 s by s plus 1. So we have to assume that there is a PI controller and we have to find the corresponding gain margins by two methods. One is if we construct a PI controller by direct synthesis method with the critical time constant 0.3 minutes, and then the second is if the phase margin is 40 degrees and if we assume the integral time to be 0.5 minute. Yeah, so if I write it, if we draw, so we are having a controller Then we are having the process transfer function. We have to construct the PI transfer function using two approaches, either using so the first is using direct synthesis and the second is using the information given below, the phase margin information. And in both cases, what will be the gain margin? Gain margin is nothing but the inverse of the critical amplitude ratio, which is the amplitude ratio at the phase crossover frequency. So we have to find the amplitude ratio, and then we have to find the gain, so the phase crossover frequency, assuming the phase angle is minus 80 degree, and then we will be getting the critical amplitude ratio, and then if we take the inverse of the critical amplitude ratio, we'll get the gain margin. So let's see how to solve the problem here. Yeah, so given we have the transfer function g of s is 2 into e power minus 0.2 s by s plus 1, and if we compare it with the first order e power minus theta s by tau s plus 1, and see that the process gain k is equal to 2, and the delay theta is equal to 0.2, and tau is equal to 1. And in the question we have been asked to construct for, let's do direct synthesis. Method. So with tau c is equal to 0.3 minutes. So if you go to your class notes, let me show you. Module 6b. And section I think it's 6.1.2. Let me cross verify. Yeah, module 6. Chapter 6a to 6.1.2. There you can find the API controller's formula using the direct synthesis method. So Kc is equal to tau by k into tau c plus theta, and tau I is equal to tau. So this is the formula given, formula derived, so you can refer your class notes for doing the derivations. So if we substitute all the values which we know, we get Kc is equal to tau is 1 by 2 into 0.3 plus 0.2, which is equal to 1. Tau y is equal to tau, which is equal to 1. So our PI transfer function will be GC and then we can write the open loop transfer function, and then we can compute the amplitude ratio and also the phase angles. Okay, we need the open loop transfer function because we are doing the frequency response analysis. GC into GB. So the controller transfer function is 1 by 1 plus S. Using the direct synthesis method, we have found this out. And then the process transfer function is 2 by S plus 1 into e power minus 0.2 to S. So now let's compute the amplitude ratio. So let me do the simplification here. S plus 0.5 to S. So we know that we substitute S is equal to I omega to do the frequency response analysis. So first the amplitude. So the amplitude ratio, root of omega square plus 1 by omega 2 by root of omega square plus 1. And then we can cancel 2 by omega. So this is our amplitude ratio. And then if we write the phase angle equation, we'll have tan inverse omega by 1 minus tan inverse infinity, because in the denominator we don't have a real part for the first term. Then the argument of a real number will be 0 minus tan inverse omega, and we saw how to do the arguments for an e power minus term. It will be just minus 0.2 to omega. So this goes cancelled. To omega. So we have to find the gain margin. So let this be equation 1. equation 2. If we substitute the phase angle is equal to minus 180 degree, which is pi radian into equation 2, we can get the crossover frequency omega pc. So let us do that. So minus pi, which is equal to minus pi by 2 minus 0.2 omega minus pi plus pi by 2 0.2 omega So if you simplify this, you will get 7.85 radians per minute. And then if we substitute this frequency into the equation 1, we get the critical amplitude ratio, which is equal to amplitude ratio of the open loop at the crossover frequency. So the equation was 2 by omega, so we have 2 by 7.85, which is equal to 0.255, and the gain margin GM is just the reciprocal of the critical amplitude ratio, so 1 by AC, which is 1 by 0.255, which is equal to 3.93. Yeah, so this completes our first subdivision. Now let's go to our second subdivision. So in our second subdivision, we have been given the phase margin as 40 degrees and tau y is 0.5 minute. It's equal to 40 degrees. Tau y, the integral time is 0.5 minute. So with this limited information, we will see how to compute the gain margin again. So we know that the definition for phase margin is phase angle at the gain crossover frequency minus 180 degree. In our case, 40 minus 180 will be equal to minus 140 degree. And tau y is 0.5 minutes. So let me write it in the next page so it's easy. Tau y is equal to 0.5. So the PID's transfer function in this case will be Kc into 1 plus 1 by 0.5 into S. In the first subdivision, we used the direct synthesis formula to compute the Kc, but in this case, we don't know the Kc. So we'll just keep it like that. And we have been given the process transfer function in the question. That is 2 by S plus 1 into e power minus 0.2, yes. So this will be our open loop transfer function now. And the amplitude ratio of the open loop will be equal to Kc into, so if you do the simplification here again, into let this be equation 3. And the phase angle of the open loop is equal to, so this can be written as 0.5 plus 0.5. So Kc will not have an argument, so tan inverse is 0.5 omega minus tan inverse infinity for the denominator because there is no real part, minus tan inverse b by a omega minus 0.2 omega. So tan inverse infinity is pi by 2. Zero 0.5 omega minus pi by 2 minus tan inverse omega minus 0.2 omega. Let's call this equation 4. And from the phase margin conditions, we know that at the gain crossover frequency, the phase angle is equal to minus 140 degrees. So it should be in radian. So minus 140 degrees to pi by 180. So this is for converting it into radians. So if we substitute at omega is equal to the gain crossover frequency, the phase angle is minus 140 degrees. So from equation 4, we can write minus 140 into pi by 180. This is for converting it into radians. Is equal to tan inverse 0.5 omega GC minus pi by 2 minus tan inverse omega GC minus 0.2 omega GC. And the only unknown variable in this equation is omega GC. So if we solve this equation in MATLAB or a scientific computer, we'll be getting omega GC is equal to 3.04 radians per minute. And we know that at the gain crossover frequency, the amplitude ratio will be equal to 1. At the gain crossover frequency, the amplitude ratio will be equal to 1. So we can use, because now we know the gain crossover frequency, we know the equation for the amplitude ratio, and the only variable in that equation was Kc, which was the unknown term for the second subdivision problem. So we know all the other, so we know omega gc is equal to 3.04 if we substitute, substitute omega gc is equal to 3.04, which is equal to omega in equation 3, and solve. So the amplitude ratio will be Kc into 3.04 square plus 1 divided by 0.5, 3.04 into 2 by root of 3.04 the whole square plus 1. So this is 3.04. So if we solve, we get the value of Kc, because we know all the other numerical values. So Kc will be equal to 1.34. So now we know all the terms in equation 2, but the question was to find the gain margin. So for gain margin, we know we should know the phase crossover frequency. So we have the equation for, so equation 4. So in that, if we substitute LHS is equal to, so we need the phase crossover frequency. So we substitute phi is equal to minus 180 degree or pi radian in equation 4 to get the phase crossover frequency. So if we substitute minus 180 degree or pi radian in equation 4, and then again solve, because that is the omega is the only variable, and if we solve, we get omega pc is equal to, or the crossover frequency is equal to 7.19 radians per minute. So we are closer to completing the problem. So the critical amplitude is equal to the amplitude ratio at phase crossover frequency. So we know, so in equation 3, using the equation, using the information given in the question, we have found the value of Kc, and also we know the value of omega, which is the phase crossover frequencies, as 7.19. So if we substitute all that in equation 3 now, what we'll end up getting is the critical frequency, and if you solve, we get, I have done all the solvings and I've verified the numerical values. So I'm writing it straight, so you get 0.383. And gain margin will be just 1 by AC, which is equal to 1 by 0.383. It's equal to 2.61. So this is the final answer. So the gain margin using the first approach was 3.93, and using the information given in the second subdivision, it was 2.61. So this completes question 3, and now let's go to question 4. Yes, so this is the final question. So it might be a bit confusing in the beginning, but if you practice a couple of times, you should get a hang of it. So let me read. So question 4 is very similar to question 3, so it will be just that we have more math to do. So we have been given the controller transfer function GC, wall transfer function GV, GP, GD, and GM. So if we draw the loop, it should look something like this, because we have a negative feedback. GC, GV, GP, and there's a disturbance. So the disturbance transfer function is GD. And then we have a measurement GM. Yeah, so this will be the closed loop structure. So we have been given GD, but when we are writing the open loop, we will not consider the disturbance transfer function because it will not appear in the multiplication of the forward blocks. So if you write the open loop transfer function, it will be just the product of GC into GV into GP into GM. So open loop GC into GV into GP into GM. KC into two S plus 1 by 0.1 S plus 1 GV 2 by 0.5 S plus 1, and then GP 0.4 by S into 5S plus 1. And then finally GM. So it's the same procedure here to write down the equation of the amplitude ratio. We substitute Z is equal to I omega first, and then take the absolute value. So the amplitude ratio of the open loop is equal to Kc into root of 4 omega square plus 1 divided by root of 0.01 omega square plus 1 into 2 will be as it is 0.25 omega square plus 1, and then 0.4 by a root of omega square will be just omega into 25 omega square plus 1, and the absolute value of 1 will be 1, so we leave it. So let this be equation. It's okay, equation 1, because this is a new problem. And now we'll write the equation for the phase angle. So this is the first thing you have to do. Like if you have given any problem to solve in the frequency response chapter, you will first write the amplitude ratio of the open loop and also the phase angle, the open loop, and then you can use the given information in the question to compute whichever value you want. So here let's start from the first term. Kc will be 0, so the argument of Kc will be 0, and then tan inverse 2 omega by 1, 2 omega minus tan inverse of 0.1 omega minus tan inverse of 0.5 omega so we have S, so in that case it will be minus tan inverse of infinity minus tan inverse of 5 omega. So 2 omega minus tan inverse of 0.1 omega minus tan inverse of 0.5 omega. Tan inverse of infinity is pi by 2 minus tan inverse of 5 omega. So let this be equation 2. And this shall be the equation for the phase angle. Now we'll use all the information which we have been given in the question to compute the unknown parameters. So in the subdivision A, so we have been given calculate the value of Kc that provides a phase margin of 30 degrees. So let's start with some phase margin is equal to 30 degrees. So we know that phase margin is equal to the phase angle at the gain crossover frequency minus 180 degree. So at omega GC is equal to 30 minus, so we'll have minus 150 degrees. And from equation 4, if we substitute minus 150 degrees in radian and solve, because omega is the unknown variables, and if we solve for omega we get the gain crossover frequency. You can check the values, I've already checked. So you might get 1.72 radians per minute. And then we know that the amplitude ratio at omega is equal to omega GC is equal to 1. So if we substitute this is equation 2, omega is equal to 1.72 radians per minute in equation 1. Yeah, the left hand side will be 1, and then omega is equal to 1.72. The only unknown variable will be Kc. So let me show. So it's equal to Kc into all the numerators. If you simplify, you might get 2.865 divided by. So there are 4 terms on the denominator. So if you simplify, you might get 1.01468. So I've already done 1.3189, 8.6579, 1.72. So different students might solve it differently, so I've solved it in a different way. So numerically the final answer should be the same. Then we get 1 is equal to Kc into 0.14376. So Kc is equal to 1 by 0.14376. You'll get the value of Kc to be 6.94. This completes the first subdivision. We have found the value of Kc. And now in our second subdivision, we have been asked to find the gain margin when Kc is equal to 10. So now we assume Kc is equal to 10. We have to find the gain margin, which is the inverse of the critical amplitude. So all the questions are like interconnected. So Kc is equal to 10. In that case, we'll know all the values in equation 1 except for omega. So that omega, so if I draw a flowchart, we have the equation for pi open loop. We substitute minus 180 degrees or pi radian. In that we'll end up getting the phase crossover frequency, and then we substitute the phase crossover frequency in the amplitude ratio of the open loop. Because we know the Kc, we know all the terms, what we'll end up getting is the critical amplitude, and then after computing the critical amplitude, if we take the inverse, we'll get the gain margin. This is what we are going to do. So first, from equation 2, substitute minus 180 degree or pi radian on the left hand side and solve. You will get the crossover frequency to be 4.05. Yeah, the important thing to note that the minus 180 degree has to go into your scientific calculator as pi radian. No, because we know the value of the crossover frequency, phase crossover frequency, we can substitute that into equation 1. Put the crossover frequency in equation 1, and if you simplify, you will get the critical amplitude ratio, and then the gain margin is just the reciprocal of the critical amplitude. This is our final answer. So we have completed all 4 problems. So this seminar was a bit lengthy, so please pause wherever you want to and then try solving. And if you have any questions, you can always drop me an email. And if you don't understand the calculations, you can ask me. And this completes seminar 9. So I'll meet you guys in the next seminar. Thank you.